Good morning. This is Professor Evans, and we're starting our chapter discussions today. And this is the first chapter, and this is an introduction to programmable controllers and how they were first used and how they have been used in the history of the last 50 years. So, back in the days before PLCs, we basically worked with relays, timers, and counters. Those devices were physical devices that we would use to automate processes. And about the time of the late 60s, early 70s, there was a move at that time to see if we couldn't automate using computers. And the problem with using computers was that you would have a huge training problem with people who have to maintain them, because you used electricians primarily to maintain industrial processes opposed to programmers. And how did you do that? So there had to be some kind of a blend between the two. So we look at what a relay actually is. And a relay is a device that takes electric signal in, closes a contact, and then you can use that contact for another purpose. So that was invented back in the early 1800s by Samuel F.B. Morse. And the reason that they needed it was because a relay was placed in the telegraph line about every 20 miles because the batteries of the day would play out at about 20 miles. In other words, your signal would die out somewhere after 20 miles. So in order to extend that electrical signal more than 20 miles, you had to put in a relay to relay the signal another 20 miles. And that's how the name relay became the name. But relays were used to automate machinery, and they were useful. People use them everywhere, and some still do. But basically, this whole idea of relay ladder logic, or logic as we look at it, is replaced by the programmable controller today. And you can do so much more with a programmable controller, basically because the synchronous nature of the PLC as opposed to the asynchronous nature of relays. So if you look at an automation system today, all the relays have pretty much been taken out, and the PLC has been put in its place. That said, you can do a lot more today than they did back in the 50s, 60s, and 70s. So we've moved away from relays. We've moved to the PLC world, and that's where we are at today. And that's why we need to study them. We also need to look at what relays are and why they were used. So the early PLCs were developed around mini computers, and they were very expensive, and they were interesting in that they were made to be very bulletproof. And there are some interesting stories because people would not accept a computer in the factory if it didn't have the same robust nature as a relay. So they had to do things to make them look like they were very robust. They painted them gold, they made them big, they made them very hardened. And one of the quotes was the guy that first invented the programmable controller, and he said here, the Programmable Control Logic Controller emphasis on design and application. And this is from author Erickson about the early PLC. The machine tool and automotive industries were large users of relay control systems. A simple machine tool would require 6 months to a year to complete. Every year, automotive manufacturing facilities would shut down for 2 to 3 months in order to implement the changes due to the new automotive models. The lost production due to these changes was significant. So there was a huge downtime because they had to replace the relays, they had to move wiring around, and if this could be made, the time delay could be made smaller, that would be very advantageous to the automotive industry, and that's exactly what happened with PLCs. He also talked about how the new machines were sold, and he said that this company called Landis decided to purchase a Modicon, which is the first program controller was named a Modicon because it was called Modular Industrial Controller, and it was from a company in Bedford, Massachusetts, of which Richard Morley was the one of the key. He was the inventor of the PLC. But anyway, said that this company called Landis, which was in Detroit, decided to purchase the Modicon units and not to use the PDP-14, which was like a computer. When Digital tried to get it back into Landis, Landis wrapped a welder cable around the 084 and poured coke over the unit. The 084 kept right on trucking. Digital retreated with grace. In other words, you had to build them tough. You had to build them so that they could take all kinds of punishment, or they were not going to be used. So they put a welding cable around it and they poured coke over it, and that sort of said to everybody, unless you can do that kind of thing, that's just an anecdotal, but if you can't be that tough, we're not going to put you in a factory. And that's what killed some of the other competition. Well, Modicon had a competitor called Allen Bradley, and Allen Bradley and Modicon duked it out for years, and finally Allen Bradley won that war. And then over in Europe we had Siemens, and Siemens was the standard in Germany, and it became the standard for most of Europe, and then kind of for the rest of the world except the United States. So we have these two giant companies, Allen Bradley and Siemens, that have basically dominated the PLC market for the last 30 years, and I'm going to talk to you a little bit about that coming up. So this was a picture of the very first PLC and the work to get that to work. And this came about because of a specification. Now, a specification is nothing more than a fishing expedition. You write a wish list and you put it out to a number of companies and you see what they come back with. And this is what happened. They came back with all these different machines that were able to basically emulate relays, timers, and counters. So the General Motors division of Hydromatic Transmission Division in Ypsilanti, Michigan, was the group that wrote that first specification. And here's some of the output from that. This is still stuff that people have. This is part of the original specification. And people still have these and these people, some of them are still alive, that wrote this stuff, and talks a little bit about it. And I copied this stuff down, and it's very interesting. So this is sort of the history of the various companies that were evaluated, and here's some of the evaluations of them. The DEC, the PDQ, and the Modicon. The Modicon is the one that actually won, but these are the three, and you can see these evaluations and how they got studied. So this was the first. That's how you get started. You always have to get started someplace. This is a picture of the programming panel of the Modicon, and as you look at it, it's nothing more than a bunch of buttons, and it's very simple, and the addressing was set with thumb switches and then buttons. So again, I just bring that to your attention that was a picture of the original programming panel. Sorry that it is not more clear, but that's the best we have today. The tape, or the way of saving the program, was sort of crude in that they had no tape system to allow you to save your program. So what they did was they had a modem that went back to the factory in Bedford, Massachusetts. So if you were wanting to save your program, what you had to do was to put the phone and attach the modem to the programmable controller, put the phone in the ear of the modem, and then push a button, and it would take the program out of the programmable controller, and it would save it back to a tape drive at the main headquarters in Massachusetts. That's how the programs are stored. And if you wanted it restored, you'd have to do the opposite. So basically, you had to have a phone line running to each of the programmable controllers that you had installed. And that's how that was done for quite a few years. So we go through the definition of a PLC, and everybody's has a definition. So this is basically NEMA's definition. I'll let you read that at your leisure. And I like the book by Liptak called Process Control, and it's a book that you'll find me quoting many times in this text. But basically, it's a good text, and it's something that you might want to buy eventually. And there's also some interest in some of the books by a fellow by the name of Arnold Zankel, who quotes Siemens and does much of the Siemens work. So basically, you can look at the Siemens side, you can look at the American side, and you can see some of the differences between the two. This is some of the evolution of the way that the PLC has evolved early. And this is from the Siemens equivalencies that they've evolved. So you can see that the two have evolved kind of differently, but in some ways a lot the same. So what was good about a PLC is ease of programming and reprogramming in the plant. It had to be able to be programmed by an electrician. Had to have all these qualities, and those have varied over the years. They've certainly gotten smaller. And they've gotten more complicated as time has gone by. Siemens did a little differently than the U.S. market did. They used as their primary language a language called statement list, and they taught it, and it is a version of assembly level language, and it's sort of unique in that it's very much like computer programming, line by line, whereas in the United States we tried to copy or emulate ladder diagrams, which was what we've been used to from the relay days. So basically, we went about it a different way, and the Germans, obviously think theirs is better, than the United States kind of thinks theirs is better. But it's right now they've kind of meshed together, and both can do either one. So also the Japanese came up with the same kind of devices, Omron and Mitsubishi. And they have PLCs as well, and we talk a little bit about that. And we go down through here and we talk about how a microprocessor is at the heart of a PLC, and what's in a microprocessor is basically what's in a PLC. And you can look at this and you can say, yeah, that looks like a microprocessor, and it's exactly. All right, so back in the 90s, there was a lot of talk that PCs, or personal computers, were going to take over from programmable controllers, or programmable logic controllers. PLCs stand for Programmable Logic Controller, PC stands for personal computer. So why didn't they, or why haven't they, or why aren't they? Well, the reason for that is basically the ruggedized nature of PLCs. In other words, they still can guarantee you that if something goes wrong, that the I/O will go to a safe state and the program will not destroy your machine or kill a person. So that's why they're very powerful, and that's why they've stuck around, is because of the unique nature of what they can do. There's no reason why you couldn't take a PC and make it into a PLC, except for the fact that you still have to pretty much guarantee these attributes. And as we become more and more safety conscious over the years, the PLC has even become more ruggedized in the idea that it can be used for safety applications in which you have to guarantee that if something goes wrong, that the machine will go to a safe state. You've got to guarantee it. And that's the whole idea of safety, is you have to guarantee that if something goes wrong, you will return to a safe state. So that's a little bit of discussion about safety. And again, an absolute safe system is not possible. We realize that. But you can approach safety, but you can approach absolute safety by being very careful in how you design your system. So how does a PLC solve logic? Well, it does this in a cyclical way. It's a scanned program, and it starts from a safe state, usually the off state. It senses the inputs, it solves the logic in the program, and it turns on or off the outputs. So that does that again and again and again and again and again. And you say, well, how often does it do this? It does it about every 5 or 3 or 2 milliseconds. So basically, you're getting this repetitive nature, and it looks like everything is being solved just like with relays. But in fact, it's like a computer program. So the first statement affects the second statement, affects the third statement, affects the fourth statement. It's exactly how a computer solves logic, statement by statement by statement. It does it repetitively. This is a scanned program. So what you're really looking at here is real-time computer programming that is emulating relay or Boolean logic. So that's how it's solved. So we have these states, the run state, the stop state, or the test state, or the single step state. But basically you have 2 states. You can either be running, or you can be in program or stopped mode. So you can stop the processor, it can be running, and it can be solving logic, and then you can stop it. Or you can go what we call to the program mode. The 2 different process program controllers have different modes, but basically it's either the program mode or which is also the stop mode, or the run mode. Richard Morley has passed away, and his obituary is at the end of this chapter, but it's just been recent, and in his latter years he put together a bunch of YouTube videos, and it might be interesting for you, if you're interested, to go back and look at some of them. And it's interesting to note some of the philosophy around the creation of the PLC and the simplicity with which it was created. And he is very articulate, but you can listen to him. He's very good listen for short periods of time. So the YouTube videos of Richard Morley are very good. So PLCs have been around since the late 60s. At first we had a rush for everybody to get in the market, and then over the time this number has thinned out. As some people drop off, others have come in, but basically through buyouts and acquisitions and bankruptcies, we have seen a lot of the early vendors drop off. There's really 3 groups now. One is the European group, and that's dominated by Siemens, but there's others in that area as well. So you'd have Siemens, and you'd have ABB, and you'd have maybe a few others, but the company in France bought Modicon eventually. That's Telemecanique. So Telemecanique is the owner of what's left of the Modicon group. In the United States, it's dominated by Allen Bradley, and in Japan, it's dominated by the Omron and Mitsubishi, and I don't know which one is better today, but those 2 vendors in Japan have basically cornered the market. So if you have a Japanese company in the transplant, it's going to be Mitsubishi or Omron. If you have an American company that's been American for a long time, you're probably going to be Allen Bradley. If you have a company that is strong ties to Europe, probably it's going to be Siemens. And you could find a mixture of any of those, but basically Siemens and Allen Bradley have dominated the market. So this shows you, and these pictorial, you think, well, these are easy to get a hold of. They're not that easy. The old ones were a little easier to get a hold of than the new ones, but they do have these published every year, and you can kind of see the different, how things have moved over the years. So basically, who was the biggest one? Well, the Other was the biggest one in 1982, but then Allen Bradley was the biggest in the world in individual companies. And Gould Modicon. Modicon had been bought out by Gould by then. They were number 2. So these are both American companies. And this third one here was Siemens. This company right here is Texas Instruments. You say, well, Texas Instruments never had a PLC. They did have a PLC for many years. And then another company called IPC ISSC. And then here's your Japanese, Omron, another Renault, and this is Mitsubishi. So here are your Japanese companies. So now let's look and see what happened between 1982 and the early 90s. See the difference? Siemens has now taken over number 1. Allen Bradley is in the number 2 spot. Mitsubishi is in number 3. Omron is number 4. AEG Modicon, now AEG has bought out Gould for Modicon, and they've dipped all the way over to here. So that gives you a little bit of an idea as to the slippage of Modicon. In the 1970s, Modicon would have been the dominant force. Now they're all the way over to here. And as we move on, there's about 10 years ago, 12 years ago, you see Siemens and Allen Bradley, Mitsubishi, Schneider, which is now this is the Modicon group, Omron. Now it's interesting that B&R is in there. B&R is a small company that's in Germany that kind of competes a little bit with these guys. So they're kind of the little guy. This is the big guy in Germany. GE Fanuc. GE has always had a PLC. SA Brown Boveri entered the market, and then there's the other ones. Now I do have the percentages on this one. This was the last one, and I was able to get the actual percentages based on this. So Siemens is at 31%, Allen Bradley is at 22%, Mitsubishi is at 13%, Schneider, which is Modicon, is back a little bit. They're not doing badly at 8%. 6% is Omron, B&R 4, GE Fanuc 3, 2 is SA Brown Boveri. But SA Brown Boveri is a big company, so even though this is small, they're a powerful company, and they can be bigger. And then the others, you say, well, what happened to some of these other people? Well, here you can look at right here, the Texas Instrument Company was bought out by Siemens about in the late 90s. So these two actually joined force. This was an American company, this is a German company, this company bought this company, so there was a buyout, and that's how they are. So if you call into the Siemens company, their helpline, you're actually calling in to the old TI company in Johnson City, Tennessee. That's why when you talk to them, you're talking to some people that used to be TI. Okay, so I want to go down here and I want to give you a statement, and I want you to think about this for a little bit. And this is from a book from Siemens, and I pose this as a challenge to people that take this course, that they look at this and they say, you know, why am I taking this course, or why is this important? So the fellow wrote, this Zankel fellow wrote, Siemens at first used STL, statement list, programming exclusively, have been very successful with it. It seemed reasonable to program something in a way people think of it and describe it verbally. High education standards in Germany and Europe also supported this approach. In the US, where training for skilled workers was generally less intensive than in other countries, the ladder diagram derived from the circuit diagram dominated from the start. So I'm going to pose that to you and say, you know, we're in competition with these folk for what we do and how we produce. So if this is true, and I think in a way it is, we have a long way to go to be competitive, and we must be competitive. So basically, we have to make up for what has been kind of done to us. So my suggestion is we study both the Allen Bradley and the Siemens approach, and we look at both and we say, I understand what you do and how you do it. Now, I can do this either way. I'm not going to be locked in to the Siemens or the Allen Bradley. Another side of this is this. If you were to go out and get a job and you were, say, an Allen Bradley programmer, a lot of people say they're Allen Bradley programmers. Whether they can program or not, they say they can. And people typically accept the fact that, well, you've been in a factory, you've worked around industry, you can do this. Whereas someone who's just coming out of school, they say, well, you have to have 3 years. You have to have been out there and proved yourself before we're going to accept you as an employee in our company. They kind of don't say that if you say that you can program Siemens, because most of the people that are saying that they can program can't program Siemens. So if you can program Siemens, you kind of go around that group of people and you get pretty much to the head of the line. That's what the goal is of this course, is to give you enough of the programming skills, both Allen Bradley and Siemens, that you can kind of go around that group that basically are just Allen Bradley programmers. If you just program Allen Bradley, you position yourself as someone who is just like, there's a million other people that are going to say the same thing. But to say that you're a PLC programmer will program Siemens as well. And they aren't that much different, and one isn't that much harder than the other one. But just to say that you have programmed Siemens seems to lift most employers to thinking, wow, they're pretty dedicated and they'll do a good job. So that said, that's why we study both. Now, if you've opted for the Codex system, and I'm not against it, the Codesys system for doing your simulations with the Raspberry Pi, you're going to find a friend here. This IEC 61131-3 is the language that is used that kind of says they all look the same. And when you go through the Siemens instructions, you'll see these statements. And I'll point them out to you as you're going through them. But there's a system of statements that IEC 61131-3 uses that also can be used by anybody. So basically, this IEC standard, international standard, came along and said, this is the way that your instructions are all going to look. And some people have adapted to those, some people haven't. Allen Bradley never did, although they claim IEC 61131-3 compatibility. They've never fully complied with these statements. You'll see the statements in the Siemens library, and I'll point them out to you. They look different, but they do the same thing. And that's why the Codesys system will look different, but it does the same thing. And that's what this language is. It's the same stuff, only the instructions look a little different. So if that is confusing, hopefully it'll be straightened out. But this is a language that basically is supposed to be vendor independent. Now, can you take a program from one computer system and put it in another? Probably not. Most of the time they won't work. But you have the idea of trying to do that, is what the 61131-3 is trying to do. It's trying to make it easier for somebody to be compatible across different vendors. But it's still, because the I/O is different, because the timing in the system is different, unless you're lucky or unless you're very careful, you're going to have discrepancies and differences, even though you might say the PLC code is the same. It's hard to say that it'll ever work, and it probably has been used occasionally, but only in the simpler systems, the ones that are easy to write anyway. But that being said, this is an attempt at making a common language across all vendor platforms. And this is an idea. This is a article by a fellow by the name of Jeremy Pollard, and it goes into telling why it's good, some of the things about it, and I just present it in here as well, and go on. Okay. So we skip through this very quickly. Okay, so if you are studying PLCs, what other types of subjects could you be studying? Well, we talk about things like distributed I/O. We'll talk about it a little bit, but it really is not a major topic of any one of our chapters. Fabricating of systems. How do you do that? Both the panel and that type of thing. We do talk about that in Chapter 9. Fault tolerant or safety systems. We do talk about that in Chapter 20. Networking between PLCs and I/O. We do talk about that a little bit in Chapter 16, but not much. Use of HMI. That is, how do you put a program together on the screen of your computer to make it so that a person can run a machine. We talk about that in Chapter 15. Ethernet. We talk about that a little bit in Chapter 16, but not much. PLCs, CNCs, and robotics. We talk about that in Chapter 17 a little. Sensors and actuators, we talk about that in a little bit in Chapter 10. We also talk about sensors a lot more in our EET 4450 course. Batching systems, we talk about that a little bit in Chapter 13. MES, manufacturing execution systems. We really don't talk about this much, but this is getting the information up to the next highest level. An ERP, again, getting the information out of the programmable controller to the next highest level so that business modelers can decide what to do with the information that they have. Some other topics that kind of rub up against us, but we don't actually talk about these, but we do need these if you're programming. Chemistry. You need to know a little bit about chemistry in order to be good at process programming. Fluid flow. Again, you need to know a little bit about it. Sizing of valves, pumps, and pipes. Statics and dynamics. Local area networks, wide area networks. Database. Automatic control. Modeling using statistical models and differential equations. Machine design. So designing of a machine, how you would put a machine together. All those are topics that rub up to, but we don't actually talk about in this course, but they are necessary to an extent if you're going to do this work in the real world. Maybe somebody else will do some of these things for you or with you, and you work with them, you work in a team. Maybe you're the only one. If you are the only one, you have to know a little bit about each of these areas. So this is a course that emphasizes ladder diagram programming of PLCs. And I put a picture in here, and I put this picture in here because this is a picture of a school that I went to in '08, and it was taken outside the actual school rooms that we had in Goppening, Germany. And I want you to look at this because these were people that were invited to come from all over the world to take a course at Siemens. And as you look at this, you may or may not be impressed with who these people are, but let me just tell you this, that about half of the people that were in here were instructors from China. Out of the 40 or so people, almost half, 19 out of the 38 or 40 people were from China. 4 were from the United States. 2 of those were 2 men that were assigned to come because there was a new Mercedes-Benz plant that was coming into their area that they had to support, and the other guy was a salesman. I'm not pictured in this picture because I was out touring around that day, but I basically had been there most of the days and I was just taking a day off. But out of this also there was a group of people from Eastern Europe, included Russia, the old Eastern Bloc countries. I think Latvia was in there. I'm trying to think of some of the other countries. Turkey was there. I forget if anybody from Yugoslavia was there, but there was a lot of people from Russia and the old Eastern Bloc and in Europe, and none from the Western side, the British, French, Germany, none of them. And then from the United States, the 4 of us, and from South America, there was 6 from Mexico, and 1 from Colombia. And so those were the people that we had in this school. I think a couple of them were from Ukraine, so we had a bunch from different areas. And just when you look at it, that was one of our instructors. This was the main guy, guy from Singapore. So some of these questions you can just review if you want to. There's nothing in here that is you have to know, but one question I've asked before out of this chapter is something about names. Typically, who was the inventor of the program controller? Richard Morley, Dick Morley. Where would you find a Siemens program controller? Obviously in Europe and Germany. Where would you find a Mitsubishi? Obviously in a Japanese transplant or in Japanese manufacturing facility. Where would you find an Allen Bradley? Predominantly in the United States. But again, very simple questions, nothing major out of this chapter. But this ends this chapter, the obituary of Richard Morley, and he died in December of 2017. Excuse me, October of 2017. And so you can look at his obituary and you can see a modern day, very interesting guy. And didn't die wealthy, but he did a lot of good stuff. And so he's well remembered. And make sure that as you go through this chapter in this book, you at least realize that these are real people, and these were people that were here in the United States, and the United States actually invented this. So again, it's something that has happened over the course of the lifetime of most of your grandparents. And I remember walking into the plant at Livionsford at a young age of 22 and 23 maybe at the time, but working on a PLC, and I worked on an 084 programmable controller. So you have people of my age who have worked on these and remember the earliest days of programmable controllers. So with that, we're done with chapter 1. Take care.